Imagine this. You are sitting in your room right now. Maybe you are holding your phone, maybe you are looking at a laptop or a TV screen. The walls around you feel solid. The floor does not move. Your world seems small, familiar, and safe. Your thoughts are about things close to you: work, family, plans for tomorrow, things you can reach with your own hands. But in reality, nothing about your situation is small. You are sitting on the surface of a spinning planet, flying around a star at great speed, inside a galaxy that is drifting through the universe. Your body, your home, your city, your entire life are balanced on a tiny rock surrounded by almost infinite darkness. Welcome to Scientists Also Sleep. On this channel, we explore the real universe. No myths, no fantasy powers, no invented magic. We follow what science has discovered about reality, from the smallest scales inside your body to the largest structures in the cosmos. The truth is already strange enough. The real universe is more dramatic, more frightening, and more beautiful than most science fiction stories. In this long journey, we will slowly climb outward through the terrifying scale of the universe. By the time you reach the end of this part, your everyday sense of size and distance will already begin to break. The distance across your city will feel small. The distance across your country will feel tiny. Even the distance between Earth and the Sun, which sounds unimaginably large in daily life, will start to feel like only one small step on a much bigger map. So sit back, relax, and let your imagination travel with the story. We will move slowly and carefully, so your mind has time to adjust at each level of scale before we jump to the next. In this part, we will travel from deep inside your own body out to the edge of the sun's influence in space. Later, in the following parts of this series, we will go far beyond that. For now, we stay in what astronomers call our local neighborhood. We begin with something you know very well: your own hand. Look at your hand for a moment. You see skin, faint lines, maybe small scars, maybe a few hairs. You can clench your fist and feel the strength of muscle and bone. When you knock your knuckles on a table, it feels solid and strong. Nothing about your hand suggests that it is mostly empty space. But that is what science has revealed. If you could shrink yourself down and dive into your own hand, the first new level you would meet is the level of cells. Your skin is made of skin cells. Your blood is made of blood cells. Your muscles, your organs, your brain, your eyes, all are made of cells. Each cell is a tiny living unit, a microscopic bubble of life surrounded by a thin membrane made of fat and proteins. A single human cell is far too small to see with your naked eye. To see it clearly, you would need a microscope. Yet your body contains on the order of 30 trillion cells. That is 30 million. If you tried to count your cells one by one, saying one number every second without ever stopping to sleep, you would still not finish in a lifetime. Each cell is not just a bag of fluid. Inside each cell is a whole world. There are tiny structures that break down sugar and release energy. There are structures that build proteins. There are membranes that fold and twist to form internal compartments. There are long strands of DNA that store instructions for building and maintaining the entire body. Molecules move along microscopic tracks like trains. Chemical signals turn genes on and off. Even though a cell is so small, It is busier and more complex than a modern city. Now imagine shrinking again, going deeper inside the cell. At this smaller level, you no longer see complete cells. You see molecules. Long chains of atoms form DNA, coiling into a double helix that holds your genetic information. Other long chains fold into proteins. Some proteins act as builders, connecting pieces together. Some act as scissors, cutting molecules apart. Some act as carriers, moving oxygen or other substances from place to place. There are fats that form membranes, sugars that store energy, and countless other molecules doing specific jobs. This microscopic dance of molecules is what keeps you alive. Molecules bump into each other, react, separate, and form new combinations. They twist and fold and change shape. Everything you do, from walking to thinking to sleeping, is powered by the organized chaos of chemistry inside your cells. But even here, we are not yet at the bottom level. Zoom in again. Every molecule in your body is made of atoms. The main ones are carbon, hydrogen, oxygen, and nitrogen, with smaller amounts of many others such as phosphorus, sulfur, calcium, and iron. For a long time, atoms were imagined as tiny solid spheres, the smallest possible pieces of matter. That is why the word atom comes from a Greek word that means something like cannot be cut. Today we know that atoms are not solid and not simple. An atom has a tiny central nucleus made of protons and neutrons. Around this nucleus, electrons occupy a region of space. Old pictures show electrons as little balls orbiting the nucleus like planets around a star. In reality, electrons behave more like a fuzzy cloud, a spread-out pattern of where they are likely to be found rather than a tiny ball in one exact place. The important point for our discussion of scale is this. Almost all of the volume of an atom is empty space. If you scale an atom up so that it is as big as a football stadium, the nucleus would be a grain of sand or a small marble in the middle of the field. The electrons would be like a few tiny insects buzzing somewhere in the stands. Everything else in the stadium would be empty air. This is what repeats again and again to build your body, your chair, your walls, and the ground beneath your feet. It leads to a strange and slightly unsettling truth. You are made mostly of empty space. The chair you sit on feels firm and solid because the electrons in the atoms in your body repel the electrons in the atoms in the chair when they get too close. You never actually push atoms directly into each other. You feel forces. You are held together by invisible interactions, not by tightly packed solid matter. Our senses evolved to work at our own scale. They are not designed to perceive atoms or molecules. To your fingers, the table feels smooth and solid. To an atom, the table is an enormous cloud of emptiness filled with a very small number of particles. We have now visited a world far smaller than we can ever see directly with our eyes. It feels unreal, almost abstract. So let us turn around and start zooming out. Compared to atoms, a human being is enormous. If an atom were the size of a marble, a human body would be taller than a mountain. But you do not feel enormous. You feel normal because you compare yourself to other people and to objects around you. This shows how relative scale is. You are huge compared to a bacterium, tiny compared to a building, and somewhere in the middle compared to the planet. From the scale of your body, zoom out to your home. You can walk from one room to another in a few seconds. You can cross your home in a short time. Your home feels big when you clean it, when you paint it, when you move furniture. But if you climb a hill or look down from a tall building, your home shrinks to a small shape among many other shapes. Zoom out farther to your city. From street level, a city is a maze of roads, buildings, and people. From the window of an airplane, the same city looks like a pattern of blocks and lines. Cars become moving dots. People vanish. Parks become flat green rectangles. What once felt enormous becomes tiny and delicate. Zoom out farther. Now you see your country. What matters most are mountain ranges, rivers, deserts, and coastlines. Cities are just small clusters of brightness. Roads become thin strands connecting those clusters. Borders between nations are invisible from this height unless we draw them on maps. The land does not know our political lines. Zoom out once more. Now you see the entire planet. From space, Earth is a sphere about 12,700 kilometers across. About 70% of its surface is covered by ocean. The rest is land with mountains, plains, deserts, forests, and ice. White clouds constantly shift and swirl above the surface. At night, city lights appear as faint glowing patterns on the dark side. Earth is huge compared to you. If you tried to walk all the way around the equator, you would have to travel about 40,000 kilometers. Even driving non-stop in a car would take many days. The highest mountains rise nearly 9 kilometers above sea level. The deepest ocean trenches extend about 11 kilometers below. These are big numbers in daily life. But compared to the size of Earth, they are small. The difference between the top of the highest mountain and the bottom of the deepest ocean trench is a tiny fraction of Earth's radius. If you shrank Earth down to the size of a smooth billiard ball, the highest peaks and deepest trenches would feel like gentle bumps under your fingers. The planet would feel almost perfectly smooth. This is your world. And yet in the universe, Earth is tiny. To feel that, we build a scale model. Imagine shrinking Earth down to the size of a small glass marble, about 1.5 centimeters across. Continents and oceans would be painted on its surface in tiny patches of blue, green, and brown. You can hold this marble Earth between your thumb and finger. Now add the moon. The moon is about 1/4 the diameter of Earth. On our scale, the moon would be a pea about 4 millimeters across. The real distance between Earth and the moon is about 380,000 kilometers. In our model, that distance becomes about 30 centimeters. That means if the marble Earth is on the table in front of you, the pea-sized moon would sit about the length of a forearm away. If you hold the Earth marble in one hand, someone else holding the moon pea would need to stand an arm's length away to keep the scale right. Most textbook drawings and classroom posters do not show this. They place Earth and the moon close together and draw their sizes much larger so students can see them. That is useful for teaching some things, but it hides the true scale. In reality, almost all of the space between Earth and the moon is empty. The distance from your city to another city might be a few hundred kilometers. The distance around the planet is about 40,000 kilometers. The distance to the moon is almost 10 times that. You could fly around Earth many times in the time it would take to travel to the moon at airplane speeds. Even so, the distance to the moon is still small compared to the distance to the sun. The sun is the star at the center of our solar system. It is a huge ball of hot plasma, powered by nuclear fusion in its core. Without the sun, Earth would quickly freeze into a dark, lifeless rock. The sun is about 110 times wider than Earth. If Earth is a marble 1.5 centimeters across, the sun would be a bright ball about 1.7 meters across, larger than most people. Now ask, how far away is this huge sun from the marble Earth? The real distance from Earth to the sun is about 150 million kilometers. When we shrink the system down, that distance becomes roughly 160 meters. To picture this, imagine placing the sun model at one end of a long field or a large hall. The marble Earth would be a tiny dot more than 100 meters away. Even if you know exactly where to look, it would be hard to see. Between them lies almost nothing. To understand such distances, astronomers often use the speed of light as a kind of measuring stick. Light travels at about 300,000 kilometers per second. At that speed, light can circle Earth more than 7 times in 1 second. Even so, it takes light a little over 8 minutes to travel from the sun to Earth. That means when you look at the sun, you are seeing it as it was 8 minutes ago. The image in your eyes is delayed by the time it took the light to cross empty space. If the sun could somehow vanish in an instant, Earth would not know right away. For about 8 minutes, the sky would still be bright and Earth would still feel the sun's gravity. Only after those 8 minutes would the sky suddenly go dark and the orbit change. This delay is not special to the sun. It is a basic consequence of the finite speed of light and the large size of the universe. When you look at the moon, you see it as it was just over 1 second ago. When you look at Jupiter, you see it as it was tens of minutes ago. When you look at distant stars, you see them as they were years ago. The farther you look, the deeper into the past you are seeing. Now that we understand Earth, the moon, and the sun, it is time to see the solar system as a whole. Inside the orbit of Earth are Mercury and Venus. Mercury is a small, airless, cratered world. Venus is roughly Earth's size but wrapped in a thick, toxic atmosphere with clouds of acid and a surface hot enough to melt lead. Outside the orbit of Earth is Mars, a cold desert planet with a thin atmosphere, dried-up river channels, and gigantic volcanoes that no longer erupt. Farther out is a wide region called the asteroid belt, filled with countless rocky bodies of many sizes. Some are only a few meters across. Others are hundreds of kilometers wide. They orbit the sun in a vast swarm between Mars and Jupiter. Beyond the asteroid belt is Jupiter, the largest planet in the solar system, a gas giant with stripes, storms, and dozens of moons. Saturn comes next, with its beautiful rings made of countless icy particles. Farther still are Uranus and Neptune, blue-green ice giants in the deep outer darkness. In most drawings, all these planets are shown close together so they fit on the page. In reality, the distances grow quickly. The gap between Earth and Mars is already large. The gap between Jupiter and Saturn is even larger. By the time you reach Neptune, you are about 30 times farther from the Sun than Earth is. If the Sun were a bright ball in the center of a large city, the inner planets might orbit within the urban area. Jupiter might orbit near the outer suburbs. Saturn, Uranus, and Neptune would be far out, maybe beyond nearby towns. If you laid out the solar system to scale along a highway, you would walk long distances between each small planet. Beyond Neptune lies the Kuiper Belt, a broad ring of icy bodies that includes dwarf planets like Pluto. These small, cold worlds orbit in a dim region where the Sun is only a bright star in the sky. Their surfaces are frozen, and their years are extremely long. Much farther still, scientists think there may be the Oort cloud, a huge spherical region filled with icy bodies. If it exists as we think, it surrounds the Sun in all directions, like a shell. Some comets that enter the inner solar system may come from this distant region, knocked inward by small gravitational nudges. The outer edge of this cloud might be thousands of times farther from the Sun than Earth is. Another way to think about the edge of the solar system is to look at the region where the solar wind meets the thin gas between the stars. The solar wind is a stream of charged particles flowing outward from the Sun. It creates a kind of bubble around the solar system, called the heliosphere. At some distance, the outward pressure of the solar wind balances the inward pressure of the interstellar gas. This boundary is called the heliopause. The Voyager 1 and Voyager 2 spacecraft, launched in the late 1970s, have traveled for decades through space. They have flown past the outer planets and continued outward. Both have now crossed the heliopause. They are the first human-made objects to enter interstellar space. Their radio signals are very weak when they reach Earth, but we can still receive them and learn about that remote, empty region. Even out there, beyond the planets and beyond the main flow of the solar wind, the Sun is still the main star in the sky. But compared to the vast size of our galaxy, the entire solar system is tiny. Let us pause and look back at what we have done in this part of the journey. We started deep inside your own hand, in a world of cells, molecules, and atoms. We saw that matter is mostly empty space, held together by forces. We turned around and climbed outward through your body, your home, your city, your country, and finally up to a view of Earth as a planet. We learned that Earth is large in human terms but very smooth and small on cosmic scales. We built a mental model of the Earth-Moon system with a marble and a pea separated by 30 centimeters. We stretched that model to include the Sun, a huge ball far away from a tiny Earth. We used the speed of light as a ruler and learned that light takes 8 minutes to travel from the Sun to us. Then we expanded our view to include the other planets, the asteroid belt, the Kuiper Belt, and the possible Oort cloud. Finally, we reached the heliopause, the edge of the Sun's influence. All of this, every orbiting planet and every icy rock, every region we have talked about so far, still fits comfortably inside a tiny patch of space compared to the galaxy. The terrifying thing about scale is how quickly our sense of what is huge collapses when we zoom out. Your body is enormous compared to a cell, but tiny compared to a city. A city is huge compared to a person, but tiny compared to a country. Earth feels gigantic in daily life, but it becomes a marble next to the sun. The solar system feels unimaginably large when we talk about millions and billions of kilometers. But soon we will see that it becomes a dot when we place it inside the Milky Way. For the moment, bring your attention back to yourself. You are still in your room. The walls still feel solid. The floor still seems still. But now you know that inside your body, atoms are mostly empty space. Above your head, beyond the ceiling and the sky, Earth hangs in space, spinning as it orbits the sun. The moon circles Earth at a distance that is hard to imagine. The sun shines from far away, its light taking minutes to reach you. Far beyond the sun, the outer planets, icy belts, and distant regions quietly circle in darkness. You are living on a small rock, suspended inside a vast, invisible bubble carved out by the solar wind, at the edge of a huge, cold, thin ocean of interstellar space. In the next part of this series, we will step beyond that bubble. We will talk about light years in more detail. We will meet our nearest neighboring stars. We will zoom out until the entire solar system is only a tiny dot inside a much larger structure. We will see our home star for what it really is. One ordinary star among hundreds of billions in the Milky Way. This is Scientists Also Sleep. If the distance between Earth and the Sun now feels larger and more real than before, if you can picture a marble Earth orbiting a huge sun across a field of empty space, then your sense of scale has already begun to stretch. This is only the first step in a very long journey. Until the next part, look up at the sky. Imagine the invisible architecture of the solar system above you. And remember, even when everything around you looks small and familiar, you are already living inside something vast beyond words. Imagine that you could pause your life for a moment and float high above everything. Below you, the room where you are listening becomes smaller. Your city shrinks into a pattern of lights. Your country turns into a patch of land on a curved blue world. Earth itself becomes a marble hanging in the dark, circling a star. The planets spread out around that star, tiny and cold and far apart. The solar wind stretches like an invisible bubble around all of it. And now, in your mind, you drift to the very edge of that bubble. This is where we begin. In the previous part of this journey, we started deep inside your own body. We dived down past the level of tissues and organs to the level of cells, molecules, and atoms. We discovered that you, your chair, and the entire planet are built mostly from empty space, held together by forces. Then we turned around and zoomed outward. We watched your home and your city shrink. We saw Earth as a planet, the moon as a small companion at a surprising distance away, and the sun as a huge shining ball far out in space. We explored the orbits of the planets, the asteroid belt, the Kuiper belt, the possible Oort cloud, and the heliopause, the edge of the sun's influence. All of that, as huge as it felt, was still only our local neighborhood. Welcome back to Scientists Also Sleep. Here, we keep following the trail of real science. No fantasy, no invented magic, only the best picture we have of the universe based on observation and measurement. In this part of the story, We will step beyond the comfort of the solar system. We will cross into the space between the stars, meet our nearest neighbors, and then zoom out until the entire Milky Way galaxy comes into view. By the time we are done, the solar system itself will feel small. Right now, at the edge of the sun's bubble, space is extremely empty. The heliopause, the boundary where the solar wind meets the thin gas between the stars, is far beyond the orbit of Neptune. It took the Voyager spacecraft decades to reach this region. Here, the particles streaming from the sun slow down and mix with the sparse material of interstellar space. If you could stand on an invisible platform here, what would you see? You would see blackness in every direction, dotted with stars. The sun would still be the brightest star in your sky, but it would be no longer a blinding disk. It would have shrunk to a brilliant point of light, a little brighter than the other stars, but not by much. You would not see any planets with your eyes. They would be far away and too small. The solar system, as you know it, would be reduced to a tiny glowing speck. From here, it is time to introduce a new unit of distance, the light year. Inside the solar system, we can talk about kilometers, millions of kilometers, and astronomical units. Those numbers are already hard to feel, but they are still just about manageable. Beyond the solar system, they become too small. When the emptiness between stars stretches across trillions of kilometers, it is easier to use a unit that grows out of the speed of light. Light moves at about 300,000 kilometers every second. In 1 second, a beam of light could circle Earth more than 7 times. In 1 hour, it could travel farther than any spacecraft has yet gone in its entire mission. In 1 year, moving non-stop, it covers about 9.5 trillion kilometers. That distance is what we call 1 light year. A light year is a distance, not a time. It is simply how far light can travel in 1 year. With that new ruler in hand, we can ask, how far is the nearest star beyond the sun? Our closest stellar neighbor is a small red star called Proxima Centauri. It is part of a 3-star system with 2 larger stars called Alpha Centauri A and B. The distance to Proxima Centauri is about 4.2 light years. That means that light, moving at the maximum speed allowed by the laws of physics, still needs more than 4 years to get from that star to us. Imagine riding on a beam of light that leaves the sun. In a little more than 8 minutes, you pass Earth's orbit. In a few hours, you blow past the orbit of Neptune. After a year, you are 1 light year away, far beyond the sun's outermost icy regions. You are in the deep, cold void between stars, but you are not at another star yet. You must continue at that same impossible speed for more than 3 more years before you reach Proxima Centauri. At the speeds of our current spacecraft, that journey would take tens of thousands of years. On our mental model where we shrank Earth to a marble and the sun to a large glowing ball on a field, Proxima Centauri would not fit anywhere in the stadium. It would be another ball in a completely different city, thousands of kilometers away. The space between them would be almost completely empty. This is interstellar space, a dark ocean with scattered islands of light. The sun is not special. It is one of hundreds of billions of stars in our galaxy. To understand the terrifying scale of the universe, we have to understand what kind of structure all those stars live in. Our home galaxy is called the Milky Way. We cannot fly out of the galaxy and take a photograph of it from above. Instead, astronomers have to build a picture from inside, using many kinds of measurements. When you look up on a dark night far away from city lights, you can see a faint band of light stretching across the sky. That band is the Milky Way seen from the inside. When we look along the thin disk of the galaxy, thousands and millions of distant stars blend together into a soft glow. From these observations, from the motion of stars and gas, and from radio and infrared maps, we have learned that the Milky Way is a vast, flattened disk with a central bulge. It has spiral arms that curl outward, like the arms of a spinning pinwheel. Our Sun is located in one of these arms, roughly halfway between the center and the outer edge. The size of this disk is staggering. The Milky Way is about 100,000 light-years across. That means that if a beam of light started at one edge and traveled straight across to the other edge, it would need 100,000 years to make the trip. Every second of that journey, it would be moving at 300,000 kilometers per second. Every year, it would be covering about 9.5 trillion kilometers. And still, it would need 100,000 of those years to cross the galaxy. Written human history covers only a few thousand years. Modern humans in their present form have existed for maybe a few 100,000 years. Our entire species is younger than the time it would take a single ray of light to go all the way from one side of the Milky Way to the other. This is the scale of the place we live in. Our Sun is not sitting still inside this galaxy. It orbits the galactic center, just as Earth orbits the Sun. The Sun makes one full trip around the center of the Milky Way in something like 200 to 250 million years. This huge span of time is sometimes called a galactic year. Think about that for a moment. 1 year on Earth is the time it takes our planet to go once around the Sun. You can feel that rhythm. You have lived through many such cycles. Now stretch that idea. A galactic year is the time it takes the Sun to go once around the galaxy. Since the Sun formed about 4.5 billion years ago, it has made roughly 20 such orbits. During one of those great galactic years, continents on Earth can drift and collide. Mountain ranges can rise and erode. Entire branches of life can appear, flourish, and disappear. Dinosaurs existed for more than one of the Sun's galactic orbits and then vanished. Humanity has risen only in the very last tiny slice of the Sun's latest circle around the center. Now think about how many stars share this motion. The Milky Way contains hundreds of billions of stars. Some estimates say around 100 billion. Others suggest perhaps 400 billion. The exact number is not known, but whatever the exact figure, it is enormous. A helpful mental image is again the beach of sand. Imagine walking along a beach and scooping up a handful of fine sand. Look closely at the grains. There are thousands of them in your hand. Now imagine that every grain in your hand is a star. Your palm holds a star cluster. Now look along the entire length of the beach, stretching far in both directions. There are far more grains of sand on that beach than you could possibly count. Now imagine each grain as a star. The beach becomes a model for a galaxy. This image is still imperfect, but it hints at the numbers we are dealing with. Yet even in a galaxy with so many stars, space is mostly empty. In the region around the Sun, the average distance between neighboring stars is a few light years. If you turned each star into a glowing marble and laid them out on a flat surface to scale, each marble would sit several kilometers away from the next. The galaxy is not a solid crowd of stars packed together. It is more like a thin fog of tiny lights spread across a huge volume. There are regions where stars are closer together. Globular clusters are roughly spherical swarms of hundreds of thousands of stars, bound tightly by gravity and orbiting the galaxy like satellites. If you lived in the center of one of these clusters and looked up at your sky, you might see hundreds of bright stars in every direction, much brighter and more numerous than we see from Earth. But even there, the distances between individual stars are still measured in light years. Within this vast city of stars, countless lives begin and end. Stars are born in cold, dense clouds of gas and dust. Gravity slowly pulls matter together into clumps. As a clump shrinks, it heats up and begins to spin. A disk of gas and dust forms around a central core. This core becomes a protostar. When it gets hot and dense enough in the center, nuclear fusion ignites and the protostar becomes a true star. The leftover material in the surrounding disk can stick together to form planets, moons, asteroids, and comets. These star-forming regions can be seen in the sky as glowing nebulae. Ultraviolet light from hot young stars excites the gas and makes it shine in beautiful colors. Behind the beauty lies a brutal process of collapse, heating, and radiation. The galaxy is constantly giving birth to new stars. Elsewhere, old stars are dying. Stars like the Sun eventually run out of hydrogen in their cores. When that happens, their internal balance changes. They swell into red giants, their outer layers expanding and cooling. Later, they shed those layers into space, forming planetary nebulae, and leave behind hot, dense cores called white dwarfs. These white dwarfs are only about the size of Earth but contain roughly the mass of the Sun. More massive stars live faster and die more violently. They burn their fuel rapidly and can explode as supernovae. For a short time, a single exploding star can outshine an entire galaxy. The explosion drives shock waves into surrounding gas and flings heavy elements into space. What is left at the center can be a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain, or a black hole, a region where gravity is so strong that not even light can escape. These violent deaths are not just destructive, they are also creative. The heavy elements produced in the cores of stars and in supernovae become part of the gas that forms the next generation of stars and planets. The iron in your blood, the calcium in your bones, and many other elements in your body were forged in ancient stars that lived and died long before the Sun existed. You are, in a very literal sense, made from stardust. As we look across the galaxy, we now know that many of its stars have planets. In the past few decades, astronomers have discovered thousands of exoplanets, planets orbiting stars other than our Sun. They find them by watching for tiny dips in starlight when a planet passes in front of its star, or by measuring small wobbles in a star's motion caused by the gravity of an orbiting planet. The more we look, the more planets we find. It seems that planetary systems are common. This means the Milky Way is not just a galaxy of stars. It is also a galaxy of worlds. Some may be barren rocks, some may be gas giants, some may be frozen balls of ice, some may have thick atmospheres and complex climates. On a few, conditions might allow liquid water and chemistry similar to what we know on Earth. On a smaller number, life might emerge. On a smaller number still, intelligent life might develop. We do not yet know how often this happens, but we do know that the stage on which life could appear is immense. As you listen to this, try to picture where you actually are. You are on the surface of a small planet, orbiting an ordinary star, in the thin disk of a spiral galaxy. Your star is one of hundreds of billions. Your planet is one of countless worlds. Your entire solar system, with all its planets and belts and distant clouds, would be only a tiny dot in any picture of the Milky Way drawn to scale. If the Milky Way were shrunk down to the size of your country, the whole region of space where the sun's gravity dominates would be smaller than a grain of sand. All of human history has unfolded on that grain. Now imagine that you could rise far above the galaxy and watch it in extreme time lapse. Millions of years pass in seconds. The spiral arms appear to turn slowly. Stars trace graceful paths around the center. Bright flashes of supernovae flicker here and there, like brief sparks in a deep night. Dark lanes of dust drift and twist. Small galaxies are pulled in and torn apart, their stars joining the larger structure. Gas clouds collapse, glow, and disperse. The whole galaxy looks almost alive, but its heartbeat is measured in millions and billions of years. From that perspective, your entire life is shorter than a blink. This might feel unsettling. It might even feel scary. You are not important to the galaxy. The Milky Way does not notice your existence. It has been slowly rotating for billions of years and will continue long after you are gone. But there is another way to look at it. The same laws of physics that govern the motion of stars and gas also govern the atoms in your body. The same processes that light up stars created the elements that make your brain. The galaxy has produced at least one world, this world, where matter has become able to ask questions about the place it lives in. You are a small part of the universe that has become aware of itself. The terrifying scale of the galaxy does not erase your existence. It sets the background against which your existence becomes even more remarkable. Now let us gently come back down from that imaginary vantage point above the Milky Way. You are once again in your room, listening. The ceiling above you hides the sky, but the galaxy is still there. The sun is still moving along its slow orbit around the center. The nearest stars are still scattered a few light years away. The Milky Way still stretches 100,000 light years from end to end. Inside your mind, however, something has changed. You may now feel that the word far means something different. The distance to the nearest town feels tiny compared to a light year. The distance from Earth to the sun feels small compared to the width of the galaxy. The solar system feels like a neighborhood, not like the entire universe. So far in this journey through scale, we have moved from atoms to your body, from your body to your planet, from your planet to your star, and now from your star to your galaxy. At each step, what once felt huge has become small. At each step, we have discovered more emptiness and more structure. And we are still not done. Beyond the Milky Way lie other galaxies, other groups of galaxies, and vast structures that span hundreds of millions of light years. The Milky Way itself, with all its stars and planets, is only one piece of a much larger cosmic web. In the next part of this series, we will leave the Milky Way and travel into that greater structure. We will see our galaxy alongside its neighbors. We will look at clusters and superclusters of galaxies. We will sketch the shape of the observable universe and feel just how small even 100,000 light-year wide galaxy really is. For now, pause and let your mind rest on one simple image. You are a person on a planet around a star in a galaxy. This is scientists also sleep. If after listening to this, the stars in the night sky look less like points on a flat ceiling and more like distant suns scattered through a vast rotating disk, then your sense of scale has already grown. There is still much more to explore. Until the next part, look up when you can. Imagine the slow orbit of the sun around the galactic center, and remember, you live in a galaxy of hundreds of billions of stars, and you are part of its story. Close your eyes for a moment and imagine the Milky Way from far above. You see a vast, flat disk of light like a glowing pinwheel hanging in the dark. Spiral arms curl outward from a bright central bulge. Dust lanes twist through the disk like dark rivers. Tiny points of light are scattered everywhere. Each of those points is a star. Many of those stars have planets. Somewhere on a small planet in one of the arms, there is you, listening to this. In your mind, hold that image of the Milky Way as a whole. Now, gently zoom out a little farther. As you do, something surprising happens. The Milky Way is no longer alone. Other patches of light appear nearby. They are galaxies too, each one a collection of stars, gas, and dark matter. Some are large spirals like the Milky Way. Some are small and irregular. Some are smooth and oval-shaped. You are beginning to see that a single galaxy by itself is not the end of the story. In the previous parts of this journey, we moved from atoms inside your body up to your planet, from your planet to your star, and from your star to your home galaxy. We learned that the solar system, with all its planets and distant icy regions, is tiny compared to the Milky Way. Now we are going to take the next step. We are going to leave the Milky Way and see what lies beyond. Welcome again to Scientists Also Sleep. We keep following the trail of real science, building a picture of the universe step by step. No fantasy, no invented magic, only what careful observation and reasoning suggest is true. The farther we go, the more the word big begins to lose its meaning. The terrifying scale of the universe becomes harder and harder to hold in your mind. But we will try. The Milky Way is not floating alone in empty space. It belongs to a small family of galaxies known as the Local Group. The largest members of this family are the Milky Way and the Andromeda Galaxy. There is also a smaller spiral galaxy called Triangulum, and many dwarf galaxies, each containing far fewer stars than the big spirals. The distance between these galaxies is enormous. Andromeda, our nearest large neighbor, is about 2.5 million light-years away. That means that when we look at Andromeda in the night sky through a telescope, we are seeing it as it was 2.5 million years ago. At that time on Earth, there were no cities, no written language, no history books. Early humans and their relatives were just beginning to walk the land. Imagine a beam of light leaving Andromeda and heading toward the Milky Way. It travels year after year, crossing the dark space between galaxies. For 2.5 million years, it continues forward without rest. Only then does it arrive at Earth and strike the mirror of a telescope or the surface of your eye. On a scale model, if the Milky Way were shrunk down to the size of a dinner plate, Andromeda would be another dinner plate a few meters away. The space between them would be mostly empty. The smaller dwarf galaxies would be like coins and grains of sand scattered around the plates. This collection of galaxies, bound together by gravity, is the local group. It contains dozens of galaxies. Some orbit the Milky Way, some orbit Andromeda, some drift on their own within the shared gravitational field. All of them are falling very slowly toward one another over billions of years. In the distant future, the Milky Way and Andromeda will collide and merge. This does not mean stars will crash into each other like cars in a traffic jam. There is too much empty space between stars for that to be common. Instead, the galaxies will pass through each other. Their stars, orbits twisting and reshaping under gravity. Over time, they will settle into a new, larger galaxy, perhaps more like a smooth oval than a spiral. The night sky on any surviving planet will look completely different. Even this dramatic event is just a small part of a much larger pattern. The local group is not isolated. It is one small node in a larger structure of galaxies. If we zoom out farther, we see that galaxies gather into clusters, and clusters gather into superclusters. Our local group sits on the outskirts of a larger cluster of galaxies called the Virgo cluster. The Virgo cluster contains thousands of galaxies bound together by their mutual gravity. Many of them are massive ellipticals and spirals. The cluster is tens of millions of light-years across. In its center, gravity is strong enough to hold a dense population of galaxies together. At its edges, galaxies fall slowly inward. But even the Virgo cluster is not the end of the story. Clusters themselves are part of even larger patterns. The Virgo cluster, the local group, and many other groups and clusters are part of a giant region of the universe, sometimes called the Laniakea supercluster. This supercluster spans hundreds of millions of light-years. It contains many galaxy clusters connected by filaments of matter, all slowly flowing under the pull of gravity. At this scale, individual galaxies are nearly invisible. What matters are the shapes formed by thousands of them together. To understand what the universe looks like on these scales, astronomers run large computer simulations and map the positions of galaxies across huge volumes of space. When we do this, a surprising pattern emerges. Matter in the universe does not spread out smoothly like fog. It forms a kind of three-dimensional web. This structure is known as the cosmic web. In the cosmic web, Long filaments of galaxies stretch across space like glowing threads. At the intersections of these threads, galaxy clusters gather into bright knots. Between the filaments and knots are enormous empty regions called voids. A single void can be hundreds of millions of light years across, containing almost no galaxies at all. If you could see the cosmic web directly, it might remind you of the pattern of soap bubbles pressed together, or the network of neurons in a brain, or the roots of a plant seen in 3 dimensions. Bright, dense regions are connected by thinner strands. Large holes open between them. It is a structure that repeats on many scales. In this web, the Milky Way is a small piece of one filament, part of one node. To feel the scale, imagine that each galaxy is reduced to a tiny dot of light. A cluster would then be a dense cloud of dots. A supercluster would be a long, twisting shape full of dots. The entire cosmic web would be a delicate pattern made from billions of such dots, stretching out in all directions. And this web fills the observable universe. The observable universe is the part of the universe we can, in principle, see from Earth. Its size is limited by 2 things: the finite speed of light and the finite age of the universe. Light has only had so much time to travel since the universe began. Any object whose light has not had enough time to reach us lies beyond our horizon. The universe is about 13.8 billion years old. You might think that means the observable universe has a radius of 13.8 billion light years. But space itself has been expanding while light has been traveling. Because of that expansion, the current distance to the farthest regions we can observe is larger. When we take that into account, the radius of the observable universe works out to be about 46 billion light years. That means that if you draw a sphere centered on Earth, with a radius of about 46 billion light years, everything inside that sphere is, in principle, observable. Everything outside it is, for now, beyond our reach. Light from those regions has not had enough time to reach us. Inside this sphere, astronomers estimate that there may be on the order of 2 trillion galaxies. The numbers here are so large that they almost stop meaning anything. One galaxy can already contain hundreds of billions of stars. 2 trillion galaxies multiplied by hundreds of billions of stars, each gives a number of stars that is simply beyond direct human imagination. We can try to build analogies, but they quickly become absurd. If each galaxy in the observable universe were a single grain of sand, you would need mountains and mountains of sand to represent them. If each star were a grain of sand, you would need more sand than fits on all the beaches of Earth. At this point, our language is straining. We can say the words, but our brains cannot picture the true quantity. And yet all of this, the cosmic web, the clusters, the superclusters, the billions and trillions of galaxies, still fits inside the observable universe, which is itself just the part of the universe we can see. The universe beyond that horizon may go on much farther. It may even be infinite. We do not know. What we do know is that, in this vast structure, the place you occupy is very small. From your position in a room, Earth feels large. From orbit, Earth is a small blue ball. From the distance of the outer planets, Earth is a tiny pale dot. From the edge of the solar system, the sun and its planets shrink to a star-like speck. From the scale of the Milky Way, the solar system is smaller than a grain of dust in one spiral arm. From the scale of the local group, the Milky Way is a single bright smudge among many. From the scale of the cosmic web, your entire galaxy is almost invisible, one faint dot in a thread of light. And you are somewhere inside that faint dot. This is the terrifying scale of the universe pushed to its spatial limits. It can make you feel very small. It can make your daily worries seem insignificant. Compared to hundreds of millions of light years, the distance to your workplace is nothing. Compared to billions of years, the length of a human life is a heartbeat. It is tempting to think that small means unimportant, but that is only one way to look at it. You are small compared to the universe, but you are not separate from it. You are made from its matter. The atoms in your body were forged in stars that lived and died long ago. The forces that hold galaxies together also shape the electrons in your cells. The same physical laws that govern the behavior of the cosmic web also govern the neurons in your brain as you listen and imagine. The universe is not something out there that you merely observe. You are a tiny piece of it looking back on the whole. Right now, as you hear this, you are aware of structures that span tens, hundreds, and billions of light years. You carry in your mind a mental image of the cosmic web, of clusters and superclusters, of an observable universe with a radius of tens of billions of light years. No other animal on Earth, as far as we know, holds a map like that in its thoughts. That awareness does not change the size of the universe. It does not make you physically larger, but it does mean that within this huge system there are regions, small, fragile regions, where the universe has become conscious of itself. For a moment, let that sink in. You are on a planet, around a star, in a galaxy, in a cluster, in a supercluster, in a cosmic web, inside an observable universe. And you are capable of understanding those words. So far in this journey, we have focused mostly on space, on size and distance. But there is another dimension in which the universe is enormous: time. The structures we have described did not appear all at once. They grew and changed over billions of years. The early universe looked very different from the one you live in now. To complete the picture of scale, we need to talk about time on a cosmic level. In the next part of this series, we will turn our attention to the history of the universe. We will compress nearly 14 billion years into a single mental year and see when galaxies formed, when stars lit up, when Earth was born, when life appeared, and when humans arrived. We will discover that in terms of time, we live in the last moments of a very long story. For now, hold on to one simple sentence. You are here. A person on a planet, around a star, in a galaxy, in a web of galaxies, in an observable universe whose size your mind can barely hold. This is scientists also sleep. If after hearing this, the word universe feels heavier, bigger, and more mysterious than before, then your sense of scale has grown again. There is still more to explore, not by traveling across space, but by expanding your understanding. Until the next part, when you look up at the night sky, Remember that every point of light is part of a structure far larger than any galaxy alone, and that you are watching just one tiny patch of a web that stretches as far as you can see. Think for a moment about how long a single day feels when you are waiting for something. An hour can feel slow. A week can feel long if you are counting the days to a special event. A year can feel like a major chapter of your life. 10 years can carry enormous change. Your personal sense of time is built from school years, jobs, relationships, seasons, and memories. It is a human scale of time. Now try to imagine 100 years, 1,000 years, 10,000 years. Already, those numbers begin to feel abstract. No one lives long enough to experience them directly. History books and old ruins are how we connect with centuries. After a certain point, our normal sense of time breaks down. The universe does not share our sense of time. The universe is about 13.8 billion years old. That number is so large that it is almost impossible to feel. You can say the words, but your mind cannot walk across that span step by step. To understand the terrifying scale of the universe, we not only have to stretch our idea of size and distance, we also have to stretch our idea of time. Welcome back to Scientists Also Sleep. So far in this journey, we have explored the universe by zooming out in space. We dived inward to atoms inside your body, then climbed outward through your planet, your star, your galaxy, and finally the vast web of galaxies that fills the observable universe. At each step, what once felt huge became small in a larger context. In this part of the story, we will move in a different direction. We will travel along the timeline of the universe, from its beginning to the present. We will see when galaxies formed, when stars lit up, when our solar system was born, when life appeared on Earth, and when humans arrived. By the end, you may feel that your own lifetime is both smaller and more precious than you realized. To begin, we need a way to compress deep time into something we can think about. One useful trick is called the cosmic calendar. Imagine taking the entire history of the universe, from the beginning up to right now, and compressing it into a single calendar year. The Big Bang happens at midnight on January 1st. The present moment is the last second before midnight on December 31st. Every month, every day, every minute on this imaginary calendar represents millions of years of real time. This is not a perfect model, but it helps our minds hold onto the story. On this cosmic calendar, each month stands for a little more than 1 billion years. Each day stands for about 38 million years. Each second on New Year's Eve stands for about 440 years of real time. Keep that in mind as we move through the year. Now, let us roll the calendar back to the very beginning. At midnight on January 1st in our compressed year, the universe begins in an extremely hot, dense state. This is what we call the Big Bang. It is not an explosion in space. It is the rapid expansion of space itself from a very compact, energetic state. In the first tiny fraction of a second, conditions are so extreme that we can only describe them with a mix of general relativity and particle physics. Matter and energy are intertwined. Particles appear and disappear. Forces behave differently than they do today. As the universe expands, it cools. In the first minutes of January 1st on our cosmic calendar, the basic building blocks of matter begin to form. Protons and neutrons come together to make the simplest atomic nuclei: hydrogen, helium, and a little bit of lithium. The universe is still too hot for atoms with electrons to exist. Instead, it is filled with a glowing plasma of particles and light. For a long time, the universe remains like this: hot, dense, and glowing. As space continues to expand, the temperature drops. After hundreds of thousands of years of real time, which is still early on our cosmic calendar, something important happens. Electrons slow down enough to be captured by atomic nuclei. Atoms form. The universe becomes transparent to light. Photons that were previously constantly scattered can now travel freely. This moment leaves behind a faint afterglow that still fills the universe today. We call it the cosmic microwave background. It is like a baby picture of the universe, showing tiny variations in temperature and density that would later grow into galaxies and clusters. On our cosmic calendar, this transition happens sometime in early January. For a long stretch of time after that, the universe has no stars and no galaxies yet. It is filled with dark matter and ordinary matter, mostly hydrogen and helium gas, with small differences in density spread throughout. Gravity slowly pulls slightly denser regions together. As they collapse, they heat up and spin. This process takes hundreds of millions of years. The universe is dark during this time, except for the faint glow of the cosmic background radiation, which has shifted to longer wavelengths and become invisible to human eyes. Astronomers sometimes call this period the cosmic dark ages. In the middle of our cosmic January and February, in this compressed year, gravity continues its slow work. Eventually, some of the collapsing clouds of gas become dense enough at their centers for nuclear fusion to ignite. The first stars are born. When the first stars light up, the universe's dark ages begin to end. These first stars are very different from our sun. They are thought to be extremely massive, hot, and bright, burning through their fuel quickly. They live short lives, only a few million years, before they explode as powerful supernovae. Their radiation changes the state of the gas around them, and their explosions spread heavier elements into space. As more and more stars form in many places, they begin to gather into the first galaxies. These are not yet the well-shaped spirals and ellipticals we see today. They are small and irregular, merging frequently with each other under gravity's pull. The universe is busy, chaotic, and full of violent processes. On our cosmic calendar, this era of first stars and young galaxies fills much of the first few months. By late March and April on this imaginary year, galaxies are becoming more common and more structured. Over billions of years, they grow by swallowing smaller galaxies and by forming new stars from fresh gas. Somewhere in one of these forming galaxies, our own home galaxy, the Milky Way, is taking shape. The Milky Way probably began as smaller proto-galaxies that merged together. Over time, its disk formed, spiral arms developed, and its central region grew more dense. Out in the halo around the galaxy, globular clusters and old stars trace the early history of these mergers. On the cosmic calendar, the Milky Way's main structure may be forming around late spring to early summer, perhaps in May or June. Inside one of its spiral arms, clouds of gas continue to collapse into new generations of stars. Among those stars, much later, will be the one we call the Sun. The Sun is a relatively late arrival in cosmic time. On our compressed calendar, the Sun forms around early September. In real time, this corresponds to about 4.5 billion years ago. Before the Sun existed, countless other stars had already lived and died. Their explosions scattered heavy elements into the galaxy. That enriched gas is what our star and its planets are made from. When a cloud of gas and dust collapsed to form the Sun, it also formed a rotating disk around the newborn star. Inside that disk, small solid particles stuck together, building up into larger and larger bodies. Over millions of years, these grew into planets, moons, asteroids, and comets. Earth emerged as one of those planets, in an orbit where temperatures allowed liquid water to later exist on the surface. Early Earth was very different from the world you know. Its surface was partially molten. It was bombarded by leftover debris from the formation of the solar system. Volcanoes erupted frequently. The young sun was slightly dimmer than it is now. There may already have been water, delivered by icy bodies or released from the planet's interior. On the cosmic calendar, Earth forms around September 1st. Life, however, does not appear instantly. For a while, Earth is a harsh world. As it cools, a solid crust forms. Heavy bombardment slowly decreases. Water collects to form oceans. The atmosphere changes over time. We do not know the exact moment when life begins, but evidence suggests that simple life may have appeared surprisingly early, perhaps within a few 100 million years after Earth's formation. On the cosmic calendar, this would be somewhere in mid to late September. The first life forms are simple. They are microscopic cells, perhaps similar to bacteria and archaea. They live in oceans, in shallow water, near hydrothermal vents, or in other environments where chemical energy is available. They leave only faint traces in the rocks, chemical signatures, and tiny fossil structures. For billions of years, life on Earth remains simple. On the cosmic calendar, the months of October and much of November are dominated by single-celled life. While galaxies collide and stars are born and die across the universe, on Earth, tiny cells quietly divide, evolve, and adapt. Over time, some of them learn to capture energy from sunlight through photosynthesis. This new ability changes everything. Photosynthetic organisms release oxygen as a waste product. Over hundreds of millions of years, oxygen produced by countless microscopic cells builds up in Earth's oceans and atmosphere. At first, oxygen reacts with rocks and dissolved minerals. Later, as those sinks fill, oxygen begins to accumulate in the air. This event, sometimes called the Great Oxygenation, transforms the planet. Oxygen is toxic to many earlier life forms, but it also makes possible new types of metabolism that release more energy. It paves the way for more complex life. On the cosmic calendar, This oxygenation happens in late October and early November. Still, for a long time, Earth remains a microbial world. There are no trees, no animals, no flowers, no grass. Just oceans filled with tiny organisms and mats of microbes growing in shallow waters. Complex multicellular life appears much later. On our cosmic calendar, around mid-December, things begin to change rapidly. In real time, this corresponds to around 600 to 500 million years ago. Fossils from this period show the first animals with complex bodies. Some move, some burrow, some swim. The diversity of life increases dramatically in a relatively short geological span. This burst is sometimes referred to as the Cambrian explosion. After that, life on land slowly develops. Plants colonize the continents. Insects follow. Amphibians crawl out of the water. Reptiles arise. Forests spread. Entire ecosystems appear and disappear as continents shift, climates change, and mass extinctions occur. Dinosaurs appear around late December on our calendar, perhaps on December 26. They dominate many ecosystems for tens of millions of years. They are not monsters from myths. They are diverse animals, some small, some gigantic, living ordinary lives in ancient forests, plains, and swamps. Then, around December 30 on the cosmic calendar, disaster strikes. An asteroid about 10 kilometers across collides with Earth near what is now the Yucatan Peninsula. The impact releases an enormous amount of energy. Firestorms, shock waves, massive tsunamis, and a global layer of dust and aerosols follow. Sunlight is blocked. Plants die. Food chains collapse. Many species, including most dinosaurs, go extinct. This is one of several mass extinctions in Earth's history, but it is the one that cleared the way for mammals to become more prominent on land. After the impact in the last day or so of December on our cosmic year, mammals diversify. Some grow larger. Some return to the sea. Some climb trees. Among one branch of primates, brains become larger and behavior more complex. These primates eventually give rise to early humans. On the cosmic calendar, modern humans appear extremely late. If we imagine the last day of December as 24 hours, Homo sapiens appears only in the last minutes of that day. All of recorded human history, from the earliest writing to the present, fits into the final seconds before midnight on December 31st. Every story you know, every empire, every war, every work of art, every scientific discovery, every personal memory, every moment of your life, all take place in that tiny sliver of cosmic time. This is the terrifying scale of time in the universe. From the Big Bang at the start of January to the present moment at the last second of December 31st, the universe has been evolving. Particles formed atoms. Atoms formed stars and galaxies. Stars forged heavier elements and exploded. Galaxies grew and collided. In one galaxy, a star formed with planets. On one of those planets, life began. For most of that planet's history, life stayed simple and small. Only at the very end of the cosmic year did complex animals, forests, and finally humans appear. You are living in the last instant of a very long story. This can feel overwhelming. It can make your life seem insignificant. If the universe is so old, and if humans have existed for such a short time, does anything we do matter? That is a question each person has to answer for themselves. But there are some things we can say from the cosmic perspective. First, the fact that your life is short compared to the age of the universe does not make it less real. Time feels long or short depending on the scale you choose. To you, a minute can matter. An hour can matter. A day, a year, a decade can be full of meaning. The universe does not experience time the way you do. It does not feel boredom or urgency. You do. Second, the story that led to you is long and improbable. Countless events had to unfold in a particular way for you to exist. The formation of the Milky Way, the birth of the sun, the stability of Earth's orbit, the emergence of life, the survival of lineages through mass extinctions, the rise of mammals, the evolution of primates, the choices of your ancestors. You are the result of a chain that stretches back billions of years. Third, you are part of the universe's way of knowing itself. For most of cosmic history, there were no eyes to see galaxies, no minds to draw cosmic calendars, no instruments to detect the faint glow of the microwave background. Now, on at least one small world, there are beings who can measure the age of the universe, map the cosmic web, and understand the processes that built the elements in their own bodies. When you think about the age of the universe, you are not standing outside it. You are a small piece of it becoming aware of its own history. Right now, as you listen, the universe continues to change. Stars are being born in distant nebulae. Others are dying in supernova explosions. Galaxies are colliding in slow, silent dances. The cosmic web is stretching as space itself expands. On Earth, life is still evolving. Human societies are still changing. New ideas are forming in human minds, including yours. The terrifying scale of time does not make your moment meaningless. It shows that your moment is rare. You live at a time when the universe is old enough to have built the complexity needed for life and consciousness, but not so old that all the stars have burned out. You exist in a brief window when the night sky is full of galaxies whose light can still reach you, before the expansion of space carries them so far away that their light will never arrive. From the perspective of deep time, you are here at a very special moment. So far in this series, we have stretched your sense of size and your sense of time. We have moved from atoms to the solar system, from the solar system to the galaxy, from the galaxy to the cosmic web, and now from the beginning of the universe to the present. We have seen that, at every scale, what once felt huge becomes tiny in a larger frame. Yet at the same time, at every scale, there are structures, patterns, and stories that matter. In the final part of this journey, we will look ahead. We will ask what might happen to the universe in the far future. We will explore scientific ideas about how stars will fade, how galaxies will change, and how the universe might end or continue on timescales beyond anything we have mentioned so far. For now, hold on to one image. On the cosmic calendar, the entire history of the universe is 1 year. You are alive in the last second of December 31st. You carry, in your mind, the ability to understand the whole year. This is scientists also sleep. If after hearing this, the age of the universe feels more real, and your own lifetime feels both brief and precious, then your sense of time has stretched. There is still one more step to take into the deep future, where time itself becomes almost impossible to imagine. Until then, look at your own day, your own year, your own life, and remember, their smallness compared to 13.8 billion years does not reduce their value. It reveals how rare and unlikely it is that you are here at all. When you think about the future, your mind probably jumps to days, months, or years. You might wonder what will happen next week, next year, or 10 years from now. Maybe you imagine the future of your family, your city, or your country. If you stretch your imagination, you might think about hundreds of years ahead, or maybe 1,000. Beyond that, time becomes foggy. It is hard to picture a world 10,000 years from now. It is almost impossible to feel 1,000,000 years. Now try to imagine 1 billion years, 10 billion years, 1 trillion years. At those scales, human history disappears into a thin line. Entire mountain ranges can rise and vanish. Continents can drift across the globe and collide. Stars can be born, burn, and die. Galaxies can change their shapes and merge. Even the basic character of the universe can shift. The universe does not stop after the present moment. It keeps going. Welcome back to Scientists Also Sleep. In this journey, we have stretched your sense of size and time. We have gone from atoms inside your body to the edge of the observable universe. We have gone from the beginning of time, through the formation of galaxies, stars, planets, and life, all the way to the present, which fits into the last second of a cosmic year. We have watched the universe grow from a hot, dense fireball into a vast web of galaxies. Now, in this final part, we will look forward. We will ask what may happen to the universe in the far future. We will explore what science suggests about the fate of stars, galaxies, and the cosmos itself. Much of what we will talk about comes from combining what we know about physics with what we observe about the universe today. Some of it is more certain. Some of it is more speculative. All of it reaches far beyond any timescale we can directly experience. As we move into this deep future, remember that you are listening from a very specific moment. Early in the life of the universe, on a small planet, orbiting a still healthy star, inside a galaxy that is still full of bright, young stars. Start with something close to home, the future of the sun. Right now, the sun is in a stable phase of its life. It has been shining for about 4.5 billion years and has enough hydrogen in its core to continue shining in a similar way for several billion more. Deep inside, hydrogen nuclei are fusing into helium, releasing energy that slowly makes its way outward and eventually reaches us as light and warmth. The balance between gravity pulling inward and pressure pushing outward keeps the sun steady. But that balance will not last forever. As the sun ages, it very slowly gets brighter. Over the next few 100 million years, its energy output will increase. Even a small change in brightness can have big effects on Earth's climate. At some point, probably within the next 1 to 2 billion years, this gradual brightening may trigger a runaway greenhouse effect. The oceans could begin to evaporate. Water vapor, a powerful greenhouse gas, would trap more heat. The surface could grow hotter, and complex life would find it increasingly difficult to survive. Long before the sun physically swells into a red giant, Earth may become a hostile world. If life continues to exist, it might retreat underground into deep oceans if any remain, or perhaps off the planet entirely, if an advanced civilization has found ways to live elsewhere. But under normal conditions, Earth's comfortable habitability is temporary. It is a brief window in the long life of the sun. In roughly 5 billion years, the sun will reach a more dramatic turning point. Its core will run low on hydrogen fuel. Without enough fusion to support it, the core will contract under gravity and heat up. The outer layers will respond by expanding. The sun will swell into a red giant. Its diameter will grow many times larger than it is today. It may expand beyond the current orbit of Earth, or at least approach it closely enough to strip Earth of any remaining atmosphere and scorch its surface completely. From the point of view of life on Earth, this is the end. The oceans will have long boiled away. The crust may partially melt. Whatever remains on the surface will be sterilized. After some time as a red giant, the sun will become unstable and shed its outer layers into space. These layers will drift outward as a glowing shell of gas, lit by intense radiation from the exposed core. This beautiful but brief phase is called a planetary nebula. In the center, the small, dense core of the sun will remain. It will cool and contract into a white dwarf, an object about the size of Earth, but with about half the mass of the original sun packed into it. This white dwarf will no longer produce energy through fusion. It will shine only with leftover heat, slowly radiating that heat into space over billions and trillions of years. From Earth's perspective, the story is finished. From the universe's perspective, the story has barely begun. Across the Milky Way, countless other stars are following their own paths. Many stars like the sun will become red giants and then white dwarfs. More massive stars will end their lives more violently, exploding as supernovae and leaving behind neutron stars or black holes. Small red dwarf stars, which burn their fuel slowly and efficiently, will live far longer than the sun, perhaps for trillions of years. While individual stars are born, live, and die, the galaxies they live in are changing too. Galaxies are not still pictures. They are dynamic systems in which stars orbit, gas flows, and dark matter forms a massive, invisible framework. Gravity pulls galaxies toward one another. Over time, they merge and rearrange. Our own Milky Way is already moving toward our nearest large neighbor, the Andromeda Galaxy. Even now, in the present, Andromeda is a faint patch of light in our night sky. We know from precise measurements that it is approaching us at high speed on a collision course. The collision will not happen tomorrow. It will not even happen in the next few human civilizations. It is expected to begin in about 4 billion years, around the same time that the sun is entering its more unstable phase. When the Milky Way and Andromeda meet, what will it look like? If you could stand on a world around some distant star and watch over millions of years in fast motion, you would see two great spiral galaxies drawing closer. At first, they would appear as separate pinwheels, each with its own bright core and spiral arms. As gravity takes hold, their shapes would distort. Long streams of stars would be pulled out into tidal tails. Clouds of gas would collide, compress, and trigger new waves of star formation. Over time, the two galaxies would pass through each other, then swing back together, interacting again and again. Eventually, after a long series of close encounters and distortions, they would settle into a single, larger galaxy. Many astronomers casually refer to this future merged galaxy as Milkomeda, a blend of Milky Way and Andromeda. Its exact shape is hard to predict, but it may be more like a giant elliptical galaxy than a neat spiral. During all this, most individual stars will not crash directly into one another. The space between stars is so great that even in a galactic collision, direct star impacts are rare. Instead, stars will have their orbits changed. Some will be flung into long, thin streams. Some will fall into new orbits around the merged center. Some may be ejected entirely into intergalactic space. Our sun, if it still exists at that time, will simply be carried along. Its sky may grow more crowded and strange as new patterns of stars appear, but its immediate neighborhood might remain surprisingly calm. The real drama will be unfolding on scales far larger than any solar system. While mergers like this reshape galaxies locally, the universe as a whole is changing in another way. Space itself is expanding. We have known for about a century that distant galaxies are, on average, moving away from us. The light from them is stretched, shifting toward longer, redder wavelengths. The farther away a galaxy is, the faster it appears to recede. This pattern suggests that space is not static, it is getting larger. More recent observations have revealed something even stranger. The expansion of the universe is accelerating. Galaxies are not just moving apart at a steady rate. The rate at which they recede is increasing over time. We give the name dark energy to whatever is causing this acceleration. We do not yet know exactly what dark energy is. It behaves in some ways like a kind of energy built into the fabric of space itself. As space expands, there is more of it, and its effect becomes more significant. The consequences of this accelerated expansion are profound. Right now, we can see billions of galaxies. Light from them has had enough time to reach us, but there are regions so far away that their light, emitted today, will never catch up to us. The expansion of space will carry them away faster than light can close the gap. They lie beyond our cosmic event horizon. As time passes, more and more galaxies will cross this horizon. Their light will fade and disappear from our sky. In the very distant future, only the merged remnant of the local group, our own island of stars, will remain visible. Everything else will have slipped beyond reach. In that far future, if there are astronomers living on planets around some surviving star in the merged galaxy, their view of the universe will be very different from ours. They might see a single huge galaxy and almost nothing beyond it. The evidence we now use to deduce the Big Bang and cosmic expansion. The cosmic microwave background, the large-scale distribution of galaxies, the Hubble relation, may no longer be available to them. Reconstructing the true history of the universe could be much harder. While the universe expands and distant galaxies fade, Another slow process is unfolding, the decline of star formation. Stars form from clouds of gas. Every time a star forms and shines, it converts some of that gas into heavier elements. Some of those elements end up locked in stellar remnants or planets. Some are blown out of galaxies into intergalactic space. Over time, the reservoirs of cold gas that can easily collapse into new stars are depleted. On timescales of tens to hundreds of billions of years, star formation will slow down dramatically. Galaxies will gradually run out of the raw material needed to make new stars. The universe will move from an era full of bright, newborn stars to an era dominated by long-lived, dim stars and the leftovers of earlier generations. Cosmologists sometimes divide the universe's history into eras. The time we live in now, when stars are still forming and galaxies are bright, is part of what is called the stelliferous era, the era of stars. This era began when the first stars ignited and will continue as long as new stars are being born in significant numbers. Eventually, when star formation has nearly stopped and most ordinary stars have burned out, the universe will enter the degenerate era. In this phase, the main objects in the universe will be stellar remnants, white dwarfs, neutron stars, and black holes, plus a dwindling population of slowly fatting red dwarf stars and cold planets. Only much later, when even these remnants have either cooled or decayed, and black holes have dominated and then evaporated, does the universe enter even stranger stages, sometimes called the black hole era and the dark era. Let us move forward in thought into the degenerate era. In this far future, galaxies are quiet places. The bright spiral arms and glowing nebulae familiar from present-day images have faded. Most of the luminous stars that once populated those galaxies have long since died. What remains are dim red dwarfs, some still burning calmly after trillions of years, and a huge population of white dwarfs, cooled or cooling, along with neutron stars and black holes. The night sky of a planet that somehow still orbits a surviving red dwarf in this era would be darker than our current night sky. Fewer bright stars would be visible. The galactic background would be fainter. Still, if there were eyes to see it, it would not be entirely empty. Islands of faint light would dot the darkness. Over unimaginably long times, this population of remnants will evolve. White dwarfs will cool and fade. Neutron stars, though they do not radiate as brightly, may still slowly lose energy. Planets will be battered by occasional close encounters and gravitational interactions, thrown into new orbits or ejected into interstellar space. Some stellar remnants may collide, briefly flaring into renewed brightness. But overall, the trend is downward. Less light, less structure, more isolation. If certain theories in particle physics are correct, even the protons that make up atoms may not be perfectly stable. Some models suggest that protons could eventually decay into lighter particles over incredibly long timescales, far longer than the current age of the universe. If proton decay does happen, then there is a time in the deep future when the very building blocks of ordinary matter slowly disintegrate. White dwarfs, planets, even the atoms in your body, if they somehow endured until then, would gradually fall apart into more fundamental particles. We do not yet know if proton decay truly occurs. Experiments are still searching for signs of it. For now, it is a possibility, not a certainty, but it is one of the ideas used to sketch the very distant future. Whatever happens with protons, one type of object seems particularly durable: black holes. Black holes form when massive stars collapse or when huge amounts of matter fall into a central region of a galaxy over time. They are defined by their event horizons, boundaries beyond which nothing can escape their gravity. For a long time, black holes were thought of as eternal prisons for matter and light. Then, in the 20th century, a surprising theoretical result appeared. By combining ideas from general relativity, quantum mechanics, and thermodynamics, physicist Stephen Hawking showed that black holes should not be completely black. Quantum effects near the event horizon allow them to emit radiation very slowly. This emission carries away energy and mass. Over time, a black hole should lose mass and shrink. This process is called Hawking radiation. For large black holes, the rate of Hawking radiation is extremely small. A black hole with the mass of the Sun would take an unimaginable amount of time to evaporate completely. Supermassive black holes at the centers of galaxies, with millions or billions of solar masses, would take even longer, far longer than the current age of the universe. But time in the far future is not in short supply. If the universe continues expanding and cooling as we think it will, and if Hawking radiation is real in the way our current theories predict, then there will come a time when black holes are the last significant massive structures left. Everything else will have faded, cooled, or decayed. The universe will be dark except for the extremely faint glow from black holes slowly evaporating. Eventually, even those black holes will be gone. Their mass will be converted into very low-energy particles and radiation, spread thinly across an enormous volume of space. The universe will then be filled with a nearly uniform bath of extremely cold photons and a sparse sprinkling of other particles. This state is sometimes called the heat death of the universe. It is not literally hot. It is the opposite. The word heat here is used in a thermodynamic sense. In this scenario, the universe approaches a state of maximum entropy, where energy is so evenly spread out that there are no significant gradients left to power complex structures or processes. No new stars can form. No large-scale structures can arise spontaneously. Time still passes, but little changes. It is a strange ending. Not a dramatic fire, but a very slow fading into darkness. It is important to say again that this is one possible future, based on our current best understanding of cosmology and physics. There are other theoretical possibilities. In one alternative scenario, dark energy might grow stronger over time. If its effect increases without bound, it could eventually overcome the forces that hold galaxies together, then solar systems, then planets, and finally even atoms. In this Big Rip scenario, the universe would be torn apart on every scale in a final, catastrophic expansion. In another scenario, dark energy might change signs someday, turning from a force that drives expansion into one that pulls everything back together. The expansion of the universe could slow, stop, and then reverse. Galaxies would begin to approach each other instead of receding. Over immense time, the universe might collapse back into a hot, dense state, a big crunch. There are also ideas in which quantum effects could cause the universe's vacuum state to change suddenly, in a process called vacuum decay. In that case, a bubble of a new kind of vacuum might appear somewhere and expand at nearly the speed of light, completely changing the laws of physics in the regions it passes through. If such an event can happen, it would be unpredictable and unstoppable from our point of view. At present, the simplest models and the best available data support a gently expanding universe that heads slowly toward a heat-death-style future. But cosmology is still an active field. Future observations and theories may refine or revise this picture. Whichever of these scenarios turns out to be closest to reality, they all involve timescales that are so large that our normal sense of time breaks down. When we talk about trillions and trillions of years, we are talking about durations in which the entire history of human civilization is less than a flicker. If you wrote a timeline of the universe on a long line and tried to mark the portion containing all of human history, it would be so short that you could not see it with the naked eye. What does this mean for you, listening now? On one level, it reinforces the idea that human life is brief and small. The sun will outlive you by billions of years. Red dwarf stars will shine long after the sun is gone. Black holes will exist for longer than any star. The universe will continue changing long after humanity, and perhaps all life has vanished. On another level, though, this perspective highlights something remarkable. You are alive at a time when the universe is still young compared to the timescales we have just described. Stars are still forming. Galaxies are still bright. The night sky is full of information. Light from the cosmic microwave background still reaches us. We can still see distant galaxies and reconstruct the history of cosmic expansion. You live in a special window of cosmic time when it is possible to study and understand the universe in a way that may not be possible for beings in the distant future. You are close enough to the beginning that you can still detect its afterglow, but far enough along that complex life and intelligence have had time to develop. From the perspective of deep future cosmology, this is a very fortunate moment. Another remarkable thing is that, in spite of your smallness in space and shortness in time, you are able to hold all of this in your mind. You can think about atoms, planets, galaxies, the cosmic web, and the fate of the universe. You can imagine past and future on scales of billions of years. You can fit a map of the observable universe and a timeline of the cosmos into the limited space of your thoughts. Your brain is made of matter that was forged in stars. Your thoughts are patterns in that matter. When you think about the universe is, in a very real sense, thinking about itself. This does not change the ultimate fate of stars or the eventual fading of light, but it does give the present a kind of meaning that is not erased by the vastness of the future. Right now, you are listening to a story about the universe. That story is not outside of the universe. It is part of it. As we reach the end of this journey through the terrifying scale of the universe, take a moment to look back at the path we have traveled. We began inside your body, at the scale of cells, molecules, and atoms. We zoomed out to your planet and saw it as a marble in space. We stepped farther back to your star, the sun, and watched the solar system shrink to a tiny structure in one arm of a galaxy. We zoomed out again to see the Milky Way among other galaxies in a cluster, then among many clusters in the cosmic web, and finally as a tiny dot within the observable universe. We then turned the axis from space to time. We watched the universe expand from a hot, dense beginning. We saw the birth of the first stars and galaxies, the formation of the Milky Way, the birth of the sun and earth, the emergence and evolution of life, and the very late arrival of humans. We placed all of human history in the last second of a cosmic year. In this final part, we have looked forward into possible futures in which stars die, black holes slowly evaporate, and the universe grows dark and cold. At every step, what once felt huge turned out to be small in a larger frame. At every step, we found both emptiness and structure. At every step, we found that you are both insignificant and deeply connected to everything else. You are not the center of the universe. You are a tiny part of it, but you are a part that can understand its laws, trace its history, and imagine its future. That capacity is rare and fragile. It depends on a thin layer of life on a small rocky world around an ordinary star in one galaxy among billions. It will not last forever, but it is here now. This is scientists also sleep. If, after hearing this, the future of the universe feels vast and strange, and your own moment feels both small and precious, then your sense of scale has stretched as far as it needs to. You do not have to hold all the numbers all the time. It is enough to remember that you live in a universe with a history billions of years long and a future that may be even longer. Until you close your eyes tonight, and again when you open them tomorrow, remember this simple chain. You are a person on a planet, around a star, in a galaxy, in a web of galaxies, in an expanding universe that will continue far beyond you. And right now, in this brief moment, you are aware of it.